Hello and welcome to another episode of the EnVisioneering Exchange podcast. This is a podcast where industry leaders discuss the most important topics in HVACR. I'm your host, John Sheff. I'm Danfoss's Director of Public and Industry Affairs. You can subscribe to our show on Apple Podcasts, Spotify, SoundCloud, or wherever you get your podcasts. Today's topic is heat pumps and how they address decarbonization. And I'm thrilled to be joined by Drew Turner, Danfoss's Global Marketing Manager for Oilfree Solutions. Drew, why don't you tell us a little bit about yourself?
Yeah, thanks, John. So Drew Turner, Global Marketing Manager for Danfoss Oilfree Solutions. Been with the company for going on 6 years now. In the industry for about 23. Work in marketing, product planning, strategic planning, business development type roles throughout my career.
Great. Now, Drew, we had you on our last episode and we talked about decarbonization, electrification from a policy perspective, what states, cities, and utilities were doing. And we touched a little bit on heat pump technology, but I want to do a deeper dive and really get into some of the basics and how this technology we feel is going to really address the technology gap caused by decarbonization moving forward. Let's just jump in. What is a heat pump and how does it work?
So a heat pump basically operating on the same principle as a chiller, but in reverse. And so what you're using is the heat that's produced on the high side and utilizing the heat produced on the high side as well as potentially the cooling that's produced on the low side. But using through the vapor compression process, generating the heat on the high side, which is the primary benefit or the usage for a heat pump. And that's in general replacing traditional heating sources. So replacing, for instance, a furnace or a boiler with a heat pump to generate that heat.
Yeah, so traditionally in a lot of applications now, we have a chiller and a boiler. And this would knock the boiler part out of that. Is that right?
Absolutely. And depending on what market you're in, this is in some cases more prevalent today. In the U.S., as you mentioned, the general standard is to have two separate systems, one for the heating and one for the cooling. In Europe and in China, you see much more today, and you've seen much more in the past, where they'll try to do both with one. And so it'll switch between the two, depending on the season and depending on the primary requirement, whether it's cooling or heating. And that's the main principle that the heat pump operates on is for those applications in those markets is either providing the cooling or heating based on the primary demand. And that's as opposed to the US where based on several factors, in the past they've designed with the two different systems. One of those main factors being that you have some overlap where you need both cooling and heating at the same time.
Well, I mean, just off the top of my head, it seems more efficient to have one solution that can do both heating and cooling than two different systems. But what other efficiencies are we gaining through the move to heat pumps?
It's theoretically better from a first cost perspective to use it to do it with one instead of two separate systems. But the efficiencies that you're gaining are really, if you look at a fossil fuel fired boiler, they generally operate, and I'm talking COP or coefficient of performance, at a COP of about 0.8 to 1.2. A heat pump, based on the fact that you're taking in the heat and boosting it up to generate additional heat and higher quality heat, operates at a much higher efficiency than burning of a fossil fuel to produce that heat. And that efficiency ranges from about 3.5 to 4.5 times better than that fossil fuel fired boiler.
Yeah, so a lot more efficient, particularly on the heating side. And I think one of the other benefits is where we've seen variable speed technology on the cooling side for a long time. Now we can kind of bring it into the heating realm too, right?
Exactly. The variable speed principle doesn't really exist for a furnace or a fossil fuel fired boiler. The only part load efficiency benefit or off design condition efficiency benefit is really that you get, for example, with a fossil fuel fired condensing boiler. And that depends on your ability to drive down the condensing temperature for it. But that efficiency benefit is on the order of 5% or so, as opposed to with a variable speed drive vapor compression technology, it can get 35 to 45 to 50% better on part load efficiency. at all.
Yeah, I mean, I think that the efficiency is going to be crazy, and especially when we consider that when we're moving to electrification, decarbonization, and we're using a lot more renewables, we really need to be as efficient as possible with that electricity. And so, being able to really match supply and demand with variable speed technology is going to be key for both heating and cooling.
Exactly. That grid interactive efficient buildings, that's synonymous in our minds to the variable speed technology.
Yep. Yeah, no, I think it's going to be key and something that gets overlooked a little bit. So I think that, in my mind, I think about this stuff for commercial buildings because that's where we work mostly, but this is a residential technology too, right?
Absolutely. Yeah, heat pumps are actually pretty prevalent today on residential systems. And again, it goes back to that first Scotch driver. If you can do everything with one piece of equipment, especially for a smaller installation such as a residential, seems to make sense to everybody from the outset. And as opposed to the commercial in the U.S. in particular, where it's been kind of the standard to have two separate systems in the past, but that is changing.
So we talk about the hydronic systems for larger commercial buildings, but in the residential space, we're not pushing water around the building, right?
In the residential space, no, you're definitely not. It's your standard split systems, yes.
Yep. Yeah. So the heat pumps can take many forms and fill many applications is my point there. So I think it's very cool technology. And since you are working in the Oilfree Solutions group, how does Oilfree technology fit into heat pumps, and what can we do with that now?
So the Oilfree technology, there's a short answer to that and a long answer. I'll try to give the short one first. The Oilfree technology has in the past been designed mainly for the cooling market because that was the primary market that we saw the potential for the technology in. But you operate with magnetic bearings and centrifugal compression. And those two along with oil-free operation. And those first two factors are really what drove the focus first on cooling markets because you have some limitations with both the magnetic bearings and the centrifugal compression on the operating temperature capabilities. I kind of refer to it as more of a rifle versus a shotgun approach. A centrifugal magnetic bearing technology is optimized to the application that you design it for. Now, it can be designed also for heat pump application, and that's what we've done more recently. And so that took a combination of changes to the technology, including the optimization of that centrifugal compressor design, as well as the balancing of the forces on the magnetic bearings to allow that higher lift capability or higher differential capability that was critical for heat pump markets or applications.
Yeah, so I think there's been a lot of advances there in the oil-free technology and making these heat pumps even more efficient. I think we're going to see some very cool stuff coming out in the next couple of years. So in terms of decarbonization and the potential for these heat pumps, on the last episode, we talked about how we kind of balance what the utilities are doing with what is happening on the demand side in buildings. How does that work with heat pumps, and how can heat pumps add to that dynamic?
So if you take a electrical system that is served by a combined cycle natural gas plant, and you assume that that's your primary energy source for it, the reduction in emissions with a combined cycle plant serving an electric heat pump utilizing our technology, the emissions reduction potential is around 40% versus a condensing boiler, which is the most efficient form of that technology. The main factor that comes into play and why you see the utilities, of course, pushing for this technology in their efficiency programs is because as you integrate additional renewable resources into that grid, replacing those combined cycle natural gas plants, that emissions reduction potential goes up. So that 40% up to around 60%, depending on the heat pump application and the technology utilized. That emissions reduction potential goes up as you integrate more renewables into that grid. And so you don't have that same opportunity, of course, with the fossil fuel fired boiler. You don't significantly have the part load efficiency benefit, And therefore, you don't have the emissions reduction potential. You don't have any options with the fossil fuel fired equipment. And so that change out to the electric heat pump, which should drive both operating costs as well as emissions reduction benefits on the order of the 40% that I mentioned, with natural gas or fossil fuel fired sources at the electric utility grid, goes up incrementally as you integrate more renewables into that grid. So long term, your emissions reduction potential goes up. And that's why you see that trend today.
Yeah, I think it's really interesting how utilities and states have these very ambitious renewable energy and emissions goals, but really it comes down to getting technology like heat pumps into individual buildings and individual homes to really enable that. So I think that's a monumental task that's going to occur over many, many years.
Absolutely.
So we're talking about heat pumps in individual buildings and individual homes, but I think there's some interesting stuff, particularly happening in Europe, that we don't really see here in terms of district heating and really connecting multiple buildings or even neighborhoods or a campus into a system that really enables this technology to have its highest. Is that right?
Absolutely. As you mentioned, district energy systems are much more prevalent today in Europe. You do have them here in the US, but they're not nearly as prevalent as they are today in Europe. They started out, the interesting history, I mean, they started out here in the US about 100, 120 years ago in New York City. But since that time, that was steam systems in New York City and Boston and a couple other locations. But since that time, they've evolved in Europe. And so they started out with the same district heating systems in Europe, and they've evolved the systems to lower temperature heating system, moved away from steam a long time ago to hot water, and have incrementally lowered down the temperature of those hot water systems to reduce the losses and therefore make them more efficient. That, along with the scalability factor and as well as the thermal flywheel effect of the district energy system, which means that you have a storage capacity built into it, which gives you some resiliency that's built into that system as well. But from the generation standpoint, if you're generating heating for a district heating system for a small community in Europe, or where you do see them at a higher education facility here in the US, you have multiple options as far as the equipment and the efficiencies of those equipment that you utilize, not just with the heat pump itself, but elsewhere in the system as well. You have many more options to increase the efficiency over time and to manage that efficiency from a system level, as opposed to from an individual building level, which tends to get neglected.
Yeah, I mean, I think it's just crazy how we think of even the most efficient buildings. We're really thinking of that building as its own discrete system, when in reality, the most efficient system is really tying many, many buildings together and using the scale there to get the efficiencies. And you see that more in Europe. But even in Europe, I think district systems have only penetrated, say, 12% of the out there. So still a long way to go really all over the world. And district energy is just starting to catch on more here. And we see that at Danfoss. And like you mentioned, it's a lot on campuses, military installations, hospitals, but we don't really see it all that much in the city environment like we're talking about here. But I think it could have a much bigger role to play as we move toward decarbonization and electrification in cities, and these state and utility goals start to get more stringent.
Absolutely. You see it more prevalent in the U.S. where you have close together facilities. And you see that a lot more today than you did in the past. But in the past in the U.S., you grew out. And cities tend to grow out, less so on the East Coast than, say, in the Midwest and the South. But you see that changing here in the U.S. as well. And so that proximity of the loads, which really drove the justification for it in Europe, you see much more of that becoming prevalent today with the cities and the infrastructure being built here in the U.S.
Yeah, I think that's a really good point. Traditionally, the U.S. had very centralized electricity and systems where one central plant is going out to a lot of people in all around that plant. But in Europe and more here, we're seeing more centralized electricity generation. I think that lends itself more to some of these district systems. It's this microgrid model, and maybe that's a new name for it. But in reality, that is a sort of district energy system.
Exactly. That's exactly what it is. interactive microgrid system is exactly what this is trying to drive towards. And most people think of, whether it's a macrogrid or a microgrid, they think of electric power, but it's the thermal system that becomes much more integrated into that concept as it evolves into more of the microgrid approach too.
Yeah, and I think, one of the things that is really cool that Danfoss does, specifically in Europe, in the food retail or supermarket segment, is this utilization of waste heat and getting the waste heat from some of the commercial refrigeration equipment back into the district system. We're starting to see it more here. And I think, heat pumps can have a role to play there too, right?
Exactly. Yeah. So any source, you're looking for a heat source, and heat sources can, for a heat pump system integrated into a thermal grid, what you're trying to do is optimize the energy usage or the symbiosis of the energy usage within that microgrid. And there's multiple sources that are wasted today. With the idea with the microgrid is you analyze all those waste heat sources that are otherwise being wasted today and recover those through, just for example, a heat pump on the low side, and boost that up to serve the heating requirements either at that facility or at another nearby facility. But doing that through a district energy system is the optimal way, because then you can satisfy the load at another location based on the heat recovery at a separate facility.
Unfortunately, we're going to start seeing this stuff more and more, grid connectivity, more buildings connected together, particularly as we see more on-site renewables and storage, and we get kind of decentralized in our energy production. We're going to see more of that connectivity, buildings as a resource, and all of that. Unfortunately, a lot of this district energy infrastructure is very expensive and difficult to retrofit, involves a lot of infrastructure work. And so I worry that that ship may have sailed for us. It
is very tough. One of the primary benefits of the concept, though, is because you're leveling out the demand and supply by integrating in multiple pieces of equipment, existing equipment, you can limit the cost associated with it. For instance, if you have a downtown facility that has 2,000-ton chiller plant on it and a nearby facility that has a 1,600-ton, those were designed for 30% over the peak, or about 30% over the peak loads of those individual buildings. But if you integrate them into a district energy system, what you see is that the combination of peaks of those buildings aren't at the same time, and therefore you can meet those load requirements of those buildings without adding additional mechanical equipment. There's a scalability benefit of integrating in those individual thermal management systems of the individual buildings into a combined microgrid thermal management system.
Yeah, and I think kind of the next step, and what I'm really fascinated to see with this stuff, is how that technology, because I think technology is available, how that kind of meets with business models and how we actually get that done from a business standpoint when we're really used to looking at these buildings, both from a technology standpoint and from a financial standpoint, as kind of discrete entities. So, but that's a topic for another time. I think this has been a great discussion. We could go on and on, but let's end it there. So thanks, Drew, and we'll talk to you guys next time.
Thank you, John.
So that's it for this episode of EnVisioneering Exchange. I'd like to thank my guest, Drew Turner, Danfoss's Global Marketing Manager for Oilfree Solutions, for joining us. Don't forget to subscribe to EnVisioneering Exchange on Apple Podcasts, Spotify, SoundCloud, or wherever you listen to your podcasts. Lastly, if you enjoyed this episode, don't forget to rate, review, and share with your network. It really helps us out. Thanks for listening, and I'll talk to you next time.